Welcome back to the second part of the power system analysis. If you haven't gone through the first part of the video, you are encouraged to search it up and go through it before you join the second part of the power system analysis. Um, all right. So in the previous part, we set up the concept of KCL and we applied onto our power network, our 4-bus power network. And in this part, instead of applying the same concept on the 4-bus network, we extend it by defining a more generic network such as like this, which shows a typical connections of a bus for any network. So from the 4-bus network example, we notice that a bus can be said to be connected to any number of buses, represented by n number of buses. It can be also connected to ground and might have a current injected into it. And for the sake of generality, we will represent the current injected into the bus as II. And based on the KCL that we have established earlier, we can actually define or derive the current flow on this bus as this equation based on the KCL concept. And this equation can be rearranged according to the voltage terms, such as VI, V1, V2 until Vn. And recall that this is the self-admittance portions. This is the off-diagonal element of the admittance. And this equation, we can combine them and rewrite them in the summation form as given over here. The self-admittance part of the equation is represented by this term, and the remaining off-diagonal part of the equation is represented by this term. And this term can be further reduced into a smaller term like this, a more compact one, such as this. If we do a little bit of retracing, we will realize that this is actually equals to this and this. For example, when j equals to 1, it will be yi1 multiply v1. yi1, remember, is negative yi1 or negative y1i. So negative yi1 v1 is given to you here. When j equals to 2, it is yi2 v2, and yi2 is equals to negative yi2, such as this. All right. And if j equals to I, then you have yii vi. So when you have yii from our earlier video, we shows that yii is the self-admittance, and self-admittance is a summation of all the admittance that are connected to the bus I itself, such as this one. All the admittance connected to bus I. Admittance of this, plus this, plus this, and plus this. So, in short, this line of equation is reduced into the summation form, which can be further reduced into this most compact manner. And from your circuit analysis 1 again, you should remember that the complex power E plus JQ, as this one, is equals to VI conjugate. Okay, conjugate meaning you have to change the sign of your imaginary part from positive to negative or the other way around. In short, you toggle the sign of your imaginary number. And when you take V over, it will be P plus JQ divided by V. And when you take the conjugate over, then the P plus JQ become P minus JQ because we are the imaginary number. And for V, to as well. So the v, we notate them with the conjugate sign as this. So with this form of writing our I, and with this form of writing our I, we can say that these two are equal actually. And we can rewrite them as this. Okay, simply by taking this and equate it to this term like this. You can equally equate this to this as well, which we will use it later on. So from here, we actually realize that the equation is non-linear. So the difference between linear and non-linear can be explained by looking at a simple equation such as 2x plus 3 equals to 4. If I give you the equations of 2x plus 3 equals to 4, you're able to determine the value of the x by simply rearranging the equation. And that is what we call a linear equation, meaning that the equation that you can determine the value of the unknown directly and definitely. But this is not the case in a nonlinear equation such as this. In a nonlinear equation such as this, you are not able to determine the unknown of the equation because rearranging cannot take place, or you have multiple unknowns, which is the case in the power system analysis. So to solve a nonlinear equation, we need a slightly more advanced mathematical operations. We use the Newton-Raphson method in power flow analysis to solve our nonlinear power flow equation. And when doing so, we need to guess the value of the unknown multiple times. Or the technical terms is called, we iterate the guesswork by solving and refining the unknowns through multiple steps. So let's look at the next slide. So the next slides start with I equals to YV form. So recall this is the final form, the most compact manner of writing our I, and this is in the complex number. And in order for us to solve our Newton-Raphson, and so that we can guess our unknowns, we need to break this complex number into their polar form. So if you have forgotten the operations of the complex number, then this is a good time for you to refresh what is polar form and what is a rectangular form. This is a polar form. For example, when we break down this complex y into polar form, we will have a magnitude portion and also its phasor form. Same as y, same as v. It has a magnitude and phasor. The multiplications of two polar form is the multiplications of their magnitude and the summations of their phasor, such as this. Okay, and this is what we established earlier. I is also equals to this, and because this is also I, so this and this, they are equal, such as this. Well, in this form, we have taken our v from the left hand side to the right hand side, and then expand the complex v into polar form as well, such as this. And notice that the phasor is negative here because of the conjugate. So by default, if we do not mention, the phasor is in positive value, and because of the conjugate, the phasor now become negative. And we have two portions over here, the real part and the imaginary part. And same as this, okay? The polar form can also be broken down into the real and the imaginary part. So if you recall from your complex number operation, to break down our polar form into real and imaginary, you have to perform the cosine and the sine operation. Take for example this one. To break this down into cosine and sine operation, you simply take vi cos negative delta I plus j vi sine negative delta I. The same goes to here. yv cos delta plus cos theta plus delta plus yv j sine theta plus delta. And the cos term will be your real part, and the sine term will be your imaginary part. So if I can write this down, yes. So notice this term, vi negative delta I is actually equals to vi cos negative delta I, excuse my writing using mouse is rather not easy, plus j vi sine of the negative delta I. Okay, and it can be equals to vi, if we bring the vi together, cos delta I, cos of negative equals to positive, minus j sine of negative, you bring it out. All right, we are not going through the details of this. This is basic mathematics. Equal to this. Okay, so the same can be applied for this one. Yeah. Now, the cos part represents the real part, obviously, and the sine part represents the imaginary part. So the real part of this equation is equal to the real part over here, and the imaginary part is equal to the imaginary part over here, such as this one. Okay, such as this one. And how do you get this term over here? Notice that when you have cos negative delta I multiply with the cos of theta plus delta, it is actually equals to the cos of the summations of their angles, such as this one. So notice the theta ij come from here, negative delta I come from here, and the delta j come from here. Same as the sine over here. Okay, and because we have a negative in front of our imaginary j, when you take it over, it has a negative over here. Notice how these two terms are very similar. Apart from the cos becomes sine and the negative over here. Okay, so with this, we are able to perform Newton-Raphson method. And to perform Newton-Raphson method, we have to look into the next slide, such as this one. But don't be alarmed with the huge numbers of equations. They are simply the partial differentiation performed, okay, onto these two equations. So normally, when we solve power flow, the unknown will be the voltage value and also the angle of the voltage value, the delta. The admittance are normally given, and we normally know what is the value of the admittance. So we know what is the y and what is the theta value. So to solve for the unknown of v and the delta, so notice you have how many unknown over here? 1, 2, 3, 4. You have 4 unknown in a single equation. And you cannot solve it in one single equation, because we know that to solve 4 unknown, we need at least 4 equations. So in Newton-Raphson, in order to solve these 4 unknown in one single equation, you need to perform what we call the partial differentiation. To perform the partial differentiations of the P against V, P against Vj, P against delta I, and P against delta J. The same applies for Q. Partial differentiations of Q against Vi, Q against Vj, Q against delta I, and Q against delta J. And as you perform the partial differentiation, it will look like this. Okay, P against delta I, P against delta J, P against Vi, P against Vj. Q against delta I, Q against delta J, Q against Vi, and Q against Vj. So notice that these two are grouped together as J1 because we are differentiating P against the delta. These two are grouped as J2, P against the V, and so as the Q, J3 and J4. This J matrix, okay, is what we call the Jacobian matrix. Okay, they're called the Jacobian matrix. You are highly encouraged to go through the partial differentiation and try to derive each of these equations. Okay, they are not as complicated as they seem. They are, if you understand your partial differentiation properly and correctly. You are highly encouraged to do it and explore it on your own. Yeah. So next, based on the Newton-Raphson method, okay, the Newton-Raphson method says that the Jacobian matrix is fixed. J1, J2, J3, J4 arranged in a bigger matrix such as this. Okay, they are fixed. And if you can multiply them with the change of the delta and the V, okay, remember, we got delta over here, delta, V, and V over here. So if we can factor out the delta and the V and put it inside matrix, like this one, and multiply them together, and if these two values represents the change, we will obtain the change of P and Q as well. Okay. If we obtain the change of P and Q, then we are able to estimate what is the next value of P and Q. The same applies. If we know what is the change of delta and V, we can determine what is the next value of delta and V, such as this one. You take the change of delta plus the delta of the current value, you get the delta of the next value. You take the change of the V plus the V of the current value, you got the V of the next value. So I think it will be more clear if we can apply this onto an example such as given here. So the example we will explain in part 3 of the video. Yeah, all right. So take your time to derive the equation before we go into the example, such as this. Very important that you are able to derive it so that you can understand how the equation comes, and it helps in your application later on. And also, if you want to take your time to recall how to operate complex number, this is a good time to do it. So thank you for tuning in, and I'll see you in part 3 of the video.